Hello, this is Dr. Todd Grande. Welcome to my video on factor analysis. I have here a data set in SPSS. It's a fictitious data set, and I'm going to use it to show you how to run a factor analysis and interpret the results. So let's start by taking a look at the data. In this data set we have a variable named ID, labeled ID, and there's 100 cases. This represents 100 participants who took an assessment, and the assessment had 10 items on it. And let's just say that this assessment was designed to measure two constructs. One, depression, and items 1 through 5 were designed to assess depressive symptoms, and the other, anxiety, and that would be items 6 through 10 were designed to measure anxiety. What we use factor analysis for is to see if, among other things, if that is true. If these items load together in a way where items 1 through 5 group together, or or items 6 through 10 group together. That is, do those items have factor loadings which indicate that they stick together, they represent, they load on the same construct. Now you could also run a factor analysis without having any idea formed in advance about how the items are going to divide up. You may have some different hypotheses about how they're going to load, and if they're going to load together or not, and what ways they'll load together, but you may not know. You may not have designed the instrument with a specific factor loading model in mind. So it's more just exploratory. You want to see the constructs, or if the items load together on a particular constructs. But for the purposes of this demonstration, let's assume that we design this instrument to capture those two distinct constructs, depression and anxiety. So we would hope to see that items 1 through 5 load together and items 6 through 10 load together. So let's start by clicking Analyze. We'll go to Dimension Reduction and Factor. And you can see that, so let me put these back where they were. You can see that you have variables here. You have ID and then the 10 items. Right? So what you do is just select all and then deselect ID and then move them all over into the variables. So in a factor analysis, all the responses, all the individual values for the different items are actually entered into this, actually loaded into this variables list box. Right? So to go back for a second, these items are actual scores. So this item might be a question related to sleep patterns, which have been tied to depression. This item might be an item that asks about not having enjoyment in activities that once provided enjoyment, right? Another criteria for depression. So these are actual individual items or questions on an assessment, right? So you have to record them in this way in order to run a factor analysis. So moving back to dimension reduction and factor. So you'd have all these different items in the variables list box. For descriptives, you're going to want the initial solution, coefficients, significant levels, the determinant, and KMO and Bartlett's test of sphericity. All right, and continue. For the extraction, by default, the unrotated factor solution comes up. You also want the scree plot. And I left this to the default based on the eigenvalue of greater than 1. So this is how it decides how many factors to extract. Right? So a factor is extracted if its eigenvalue exceeds 1. Now the rotation, there's a couple different types of rotations, actually several types of rotations. Uh, but there's two general categories, right? And one is when you believe that the uh, constructs are unrelated to one another, so not correlated with one another, and one where you believe that they are correlated. And there's a lot of different views on what type of rotation to use, and of course it affects your results. But in the social sciences, in counseling, for example, it's hard to imagine a data set where you would have uncorrelated items, right? We know that in this particular instrument, we believe that the depression-related items are going to be correlated to one another, and we believe the anxiety-related items are going to be correlated to one another, but also those two groups of items, right, so are going to be correlated to each other. So, for example, item 7 still might be related to item 4, even though they load on different constructs. So in social sciences, we tend to use, I tend to use oblique rotations, and I chose the direct. If you believe they're uncorrelated, there's a different set of options, which we refer to as orthogonal, right? So that would be varimax, quartermax, equimax. And orthogonal means unrelated. So it's easy to remember in that way. It's orthogonal if you believe that they're not correlated, and it's oblique if you believe that they are correlated. So I selected the direct, and I want the rotated solution to be displayed. Scores, I did not endorse any of the options here, but you can save the scores as separate variables. And then for options, I left excluding cases listwise, which of course in this demonstration, no cases will be excluded because all the data is populated. So then at this point, you hit OK, and you first see the correlation matrix. So remembering our initial hypothesis about what we would find here, if you look at this matrix, clearly item 1 is going to correlate perfectly with item 1. But we're looking for correlations between these different items. So item 2, 0.128 with item 1, item 4, 0.338, so much stronger correlation with item 1. And similarly, if we look at item 6, you can see item 6, the correlation with item 7, quite strong, 0.542, and item 8 and item 6, 0.635. But the other correlations are fairly weak, meaning the ones that between depression and anxiety. So item 3 correlating with item 7, for example, is fairly weak, but not in every instance. See, item 3 here correlates fairly strongly, well, moderately with item 8. So what we're really looking for here is a few things. We want to make sure that the items are correlated, it gives us an idea what's going on, but we're really looking at the determinant, right? And the determinant value here is 0.044. This is one of the variables we're looking at. It has to be greater than 0.00001, so we're fairly safe here with a determinant of 0.044. If it was below 0.00001, then the items are too unrelated. The correlation's too low. Another area we want to look out for is correlations that are too high, what's called multicollinearity, right? When two items are really, the shared variance is too high, they're explaining the same thing. That's not helpful either. And the cutoff for considering an item multicollinear in a factor analysis, one cutoff that's popular is 0.8, a correlation of 0.8. And you can see that none of the values here in our correlation matrix exceed 0.8. If you have a perfect correlation outside of the obvious item 1 perfectly correlated item 1, item 2 perfectly correlated item 2, if you have a perfect correlation, that's called singularity. And obviously, in either one of those circumstances, that presents a problem, either multicollinear or if there's a singularity, and you're going to want to remove that item from the analysis. So a correlation of greater than 0.8, you're going to want to remove and change around items to eliminate that item, or one of the items in that mix that's resulting in that high correlation. Looking at KMO and Bartlett's test, you want this. We have a value here for KMO of 0.764. Anything above 0.5 is okay. Obviously, the greater the value here, the better. Similarly, with Bartlett's test of sphericity, you want statistical significance, and we certainly have it here. All right, you can see it's 0.000, which usually for writing up APA-style papers, I record this as 0.001, right? So a value less than 0.001 p-value. So you can see that the looking at the extraction here, let me move down. I'll come back up to the variance explained. You can see that there's two components that were extracted based on the eigenvalue of greater than 1. This is the eigenvalue of greater than 1. This is the discrete plot here. You can see you have 1, 2, but this third potential factor didn't meet the cutoff. So these two components, moving back up to total variance explain 52% of the variance. All right, so not ideal. Certainly a larger number here would be better, but still, you can see from the discrete plot they are above the eigenvalue of 1. Now, since we used an oblique rotation, the direct, we're going to want to interpret the pattern matrix. All right, it's not a whole lot different than the component matrix or the structure matrix, but this is the one we're going to want to look at with this particular rotation. And you can see, let's start with component 2. You can see these values load together fairly tightly. Right? These seem to represent one construct as you look here. There's not a lot of variance here. Similarly, we believe that items 6 and 10 represent a construct. In the case I have here, it was supposed to be anxiety, right? And you can see, again, these load together fairly tightly. So if you look at this pattern matrix, there does seem to be two distinct factors. So that's how you run a factor analysis and interprets results. As a reminder, I ran if you look back at going through the analysis menu selection, what was drawn here it is. Technically the method was principal components, and there is a little bit of a difference between principal components analysis and factor analysis, but oftentimes these terms are used interchangeably. But I just want to let you know that they are a little bit different, and if you want more information on that, certainly I would encourage you to explore that further. But generally, we accept the principal components analysis as achieving the same goal as the factor analysis, and we tend to use the terms interchangeably. There are many methods, as you can see here, though, for this particular factor analysis extraction. So I hope this video was helpful and allowed you to learn a little bit more about factor analysis. As always, if you have any questions or concerns, feel free to contact me, and I will be happy to assist you.